Hi everyone, this is Empawan from Data Science Branch, IARE College. Now I am here to explain you a small topic with my knowledge. So our topic is a very fast substring search algorithm. So today in this session I am going to explain you about a very fast substring search algorithm. So we'll further don't waste our time and move on to our next slides, and we will see what is the algorithm of it. Okay, yeah, here is our introduction part. This algorithm does not depend on scanning the pattern string in any particular order. Three variations of the algorithm are given that use the different patterns scan orders. These include: first one, quick quick search algorithm; next one, maximal shift algorithm; and the third and last one is optical mismatch algorithm. A fundamental technique used in computer science is to search for a specific substring in a larger body of text. Algorithms that do this rank with sorting algorithms as cornerstones of software methodology. A fundamental technique used, sorry, I'm repeating the sentence. We will move on. So I hope everyone understand this thing that we are going to discuss about three algorithms. The first one is quick search, second one is maximal shift, and the third one is optical mismatch. These three algorithms we are using for the fast string substring to get the fast substring. Okay, existing algorithms. Let P of I be the ith character in the pattern string of P of O, P of O to P of m minus 1 of length m, and let T of j be the jth character in the next string T is equal to T of 0 to T of n minus 1 of length n less n greater than m. We will assume that the pattern string T is located at position k in the text string T. In testing for a substring match, the SF algorithm is a obvious one that most programmers would see to code a substring search. The pattern string P is aligned with the extreme left of the text at position k is equal to 0, and then the pattern characters are scanned from left to right, P of O to P of 1, and so on, P of m minus 1, testing for matches against the corresponding text characters. The KMP method starts the same as the SF and scans the pattern string in the same left to right direction from P of O through P of m minus 1. When a character mismatch is found, however, between P of semicolon and T of P of 1 and T of k plus I. Additionally, a different pattern character is brought to the mismatch position. Since we already know that the current one is a mismatch, these prefix shifts for each mismatch position in the pattern string could be determined from the pattern string alone, and an initial O of m time is needed to precommutate them. The BM algorithm changes the direction of scanning the pattern string by testing the last character of it first and then producing right to left through the pattern string P of m minus 1, P of m minus 2, and so on P of 0 in testing for matches with the test. If this occurs to the left, if the position of the mismatch, then with difference is defined to be 1 for that. position in the pattern string, since most often the last character of 3 p of m-1 gives a mismatch, is generally positive. An improved algorithm. One can recode the intent of the 61 of the BM technique. First, note that the pattern string always shifts right by at least one character. Hence, the character in the text string immediately paste the end of the pattern string, namely t of k plus m, must be involved in testing for a substring match at the next position of the pattern string. This a new AR can be commutated to be the index of the first leftward occurrence of this character from the end of the text string. This either aligns that character in P with the text character T of k plus m, or when that character does not occur in P, shifts P right past it to text position k plus m plus 1. Note that this 81 is commutated as an absolute pattern shift and is not defined relative to the position in P of the last mismatch. So we will discuss about these 3 points. AL greater than or equal to 1 always, and so it can be used by itself to simply and quickly code a fast practical algorithm. The BMDL, however, is sometimes less than or equal to 0, in which case either a shift of just 1 or D2 is used. In practice, one expects that AL greater than or equal to 61 plus I. Also, whenever the last character of the pattern string matches the text character, then one expects that AL greater than or equal to 6 plus 2, and so on. This using AL results in a faster algorithm than that of BM. This is mostly true for short pattern strings, and the effect of this increase in speed decreases as the pattern string gets longer. 81 does not depend on the order in which the pattern string P is scanned. This is because it is defined relative to a text string character that lies outside the current comparison range of the pattern string. The BM61, however, depends strongly on the right to left pattern string scan order for its definition and efficient usage. This is the first algorithm. You can see this algorithm. With this, you can easily identify the sub to get the substring. So once go through this thing and you will definitely get the substring. So we will move on to next algorithm. This is also the first one is quick sorting, and this one is second algorithm for the second method. So in this method also you can search for substring. So then if a mismatch occurs testing this character, we know that the next character of P that becomes aligned with the corresponding text location must differ from P of I of O. Otherwise, there would be another mismatch. Note that if the pattern string P is scanned in the forward direction with I of P, O, 0, 1, and so on, M minus 1, then the delta 2 we have computed in the KMP also. If the pattern string is scanned in the reverse direction with I of M minus 1, M minus 2, and so on, 0, our delta 2 is the same as the BMD2. Similar to the KMP and BM algorithms, algorithm 2 should have linear O of worst case behavior for any scan order. It would seem that the KMP algorithm uses a best possible scan order for remembering already scanned text in order to avoid backtracking and produce the best worst case experience behavior. The quick search algorithm. To quickly code a fast substring algorithm, the easy to code SF pattern string scan order can be used with the easy to compute delta 1 for the pattern string shift at each stage. No delta 2 is used. This is a simple, fast, practical algorithm because it can be both coded and debugged quickly. It executes. It can be called the quick search algorithm. This simplified search algorithm is shown in algorithm 3. If one augmented this straightforward search with the delta 2 shift and added code to stop backtracking in the text, one would get a fast algorithm with the KMP algorithm tight bound on worst case behavior. The maximal shift algorithm. This is the algorithm for the max shift. So by using this algorithm, you can get the substring in an easy manner and in a quick manner without the lengthy processes. The optional mismatch algorithm. This is the last one. An algorithm that is even faster in practice can be achieved by using a pattern string scan order that optimizes the chances of getting a mismatch at each test position. This is done by ordering the characters of the pattern string P from the one least likely to occur in the text alphabet to the one most likely to occur. C code for constructing an optical mismatch ordered pattern is given in the appendix. This code sorts with a comparison of the frequency of occurrence of the pattern strings characters in the next alphabet. To illustrate the impact of the OM algorithm, note that over 20% of English words end in the letter E, the most commonly occurring character in English text, with about a 10% occurrence rate. This many words that are searched for in text using the BM algorithm often get a match for the first character tested. The table fraction of text characters tested. These are the words in the BM, OS, MS, and OM. You can easily understand this once get into it, and you will understand what are the things it was showing to you. Comparison of the algorithms. To compare the BM, QS, MS, and 3M algorithms, each was used to search for the same strings in large text buffers, and the number of comparisons made with the text characters was counted. Next, the increase in speed of the fastest algorithm, the OM algorithm over the BM algorithm, was computed as the ratio BM is to OM of the values in table 1 for each word, and the average for each pattern length was computed as shown in table 2. A further test to compare the BM and OM algorithms was done using the text buffer formed by concatenating all the Unix manual pages. The raw unformatted manual pages were only filtered by throwing away format comment lines and by converting alphabetic characters from upper to lowercase. This is the remaining two tables. Just go through it and you can understand what are the things I'm trying to explain you, and you will get to know what are the basic and main things we need to understand in this. Conclusion. So, from this, we are going to conclude. Throughout the history of computer science, has been an evolutionary discovery of new fast string search algorithms. The first of these, the QS algorithm, is very easy to implement and scans the pattern is the most natural forward order. It is almost as easy to understand code and debug as the slow, straightforward algorithm that most programs tend to use. In applications not involving English text, the algorithms presented in this article should still give better performance than the Boyer-Mori string search. The statistical on the degree of improvement could be different since they depend on the size of the text alphabet and the frequency of occurrence of the alphabet characters in the application text. So, thank you for giving me this great opportunity to share my little knowledge with you, and I hope everyone enjoyed my session. Have a great day. Thank you, one and all.